Lesson 7.4, Task 5. Model a real-world situation with a cube root function. The table and graph show a cube root function that models the cyclist's speed s in kilometers per hour that results from a given power output p in watts for a given cyclist with a calm wind. Alright, so we've got p and s of p, so it's like the same as x and y, so p and s of p. So we've got 0, 0, 30, 17.6, so on and so on. So if you take the points from the table and you put those on a graph, you can see that across the bottom it's power in watts, and up the side on the vertical axis, this is your s of p, that's in speed kilometers per hour. Alright, it says describe how the average rate of change varies over successive intervals and interpret the results in the context of the situation. Alright, the average rate of change in speed per unit of power output. Alright, let's look. So you can see that it is going from here, power output, it goes up. It is increasing, and the higher it gets, it kind of levels out and still increases, but not quite as quickly. All right, so the average rate of change in speed per unit of power output decreases from interval to interval, first quickly, then gradually more slowly, gradually more quickly. So it's going to be gradually more slowly. Weird way to write that, but okay. This means that with each given increase in power, the cyclist speed increases less and less. Alright, so you can see that the average rate of speed, see at first it's a lot, and then it's going to decrease as it gets further along the graph. So first it's quick and then it's more slowly. Alright, it says riding with a 20 kilometer per hour tailwind, the cyclist's speed is modeled by s of p equals 8. Cube root of p, compare the average rates of change for this model with those from part A. Alright, so let's just graph it. So if you've got y equals, you can click on Math and find the cube root button. So number 4 here is cube root. So let's just do the parent function, which is what we looked at first. So the cube root of x, and hit graph. So that's the cube root of x. And now we want to see how 8 times the cube root of x changes. I'm saying x, in this case it's p, but it's the same thing. Using our calculator, we're going to use x. So for the next function, I'm going to put in, oh, wait, let's go back. I need to put in 8 first. 8 times the cube root of x. And then we're going to see what that does to the parent function graph. Alright, so it makes it a lot steeper here, okay? So it says the average rate of change are greater than those for each corresponding interval for part A. So the cyclist speed increases more for a given power increase with a tailwind than a calm wind. Alright, so you can see when you put that 8, how much faster it increases. You can see that there very quickly. Alright, that is all for task 5. If you have questions, please let me know. Lesson 7.4, Task 6. Cube root or graph cube root functions. Analyze models involving radical functions. While working in sub-freezing temperatures in Antarctica in 1945, 2 scientists studied the effect of wind speed and the rate at which water turns to ice. This work eventually led to the first wind chill index used by the National Weather Service starting in the late 1960s to warn people about dangers of losing body heat on cold and windy days. The graph shows a radical function that models the first wind chill index for wind speeds from 4 miles per hour to 50 miles per hour when the air temperature is 20 degrees Fahrenheit. So the function's rule is this. And you can see where T of WC is the wind chill in degrees Fahrenheit and S is the speed of wind in miles per hour. All right, so this is your graph, and this is wind speed. You can see the wind speed as it goes from 0 to 10, 20, 30, 40, 50 degrees for wind chill, for speed of wind. You can see the wind chill here drops. So we're looking at, it starts at 20 degrees Fahrenheit, and you can see the wind chill gets colder and colder as the wind speed increases. All right, identify the key features of the radical function represented by the graph. Identify the domain of the wind chill function. The domain is your x's. So I can come over and I can say if that's 0 and 10, then I'm going to say 2, 4. It looks like 4 is the first value, and then I can see it goes all the way over to 50. All right, use the graph to identify the range of the wind chill function. All right, the range, remember, is your y values. All right, so we can see that it goes from 20 down past negative 20. So here's negative 22. So it's, well, actually, this is negative 20 and negative 40, so that means this is negative 30. So this would be negative 25. So it's halfway between negative 20 and 25. So the wind chilled decreases as the wind speed increases, starting at a maximum value of about 20 degrees Fahrenheit and ending with a minimum value of about negative 23 degrees. So the range of the wind chill goes between negative 23 and 20. All right, which of the following are true about the speed of the wind is about 12? So when the wind speed is 12, select all that apply. So let's look at the graph. Here's 10 and 20, so that each one of these would be 12. So that's where your x-intercept is. So at 12, the wind chill is going to be 0. All right, so it is an x-intercept of the graph. That's true. It's a TWC intercept. Okay, so that should be this side here. So this one is your speed. Yeah, and it says up here too, TWC is the wind chilled in degrees. S is the speed of the wind. All right, it is a 0 of the wind chill function. That is true. And the function changes from increasing to decreasing. That is not true. You can see that it's been decreasing the whole time. So it's not changing from increasing to decreasing. It's just decreasing. All right, on what interval is the function positive and what interval is it negative? Drag the intervals and explanations into the boxes. Okay, so it's positive until it gets to 12. Okay, and then after 12, it becomes negative. All right, so from 4 to 12, it's positive. And from 20 to 50, it's negative. All right, so the wind chill is greater than 0. And the wind chill is less than 0 when it goes below that line. All right, it says compare the original wind chill index with the current one. In response to complaints that the original wind chill index exaggerated the effect of wind on human skin at cold temperatures, the National Weather Service developed a new wind chilled index and started using it in the early 2000s. When the air temperature is 20, the new wind chill function is this. Graph the function using the same domain as the graph above and compare the key features. All right, so the blue line is the original function, and the red line is the new function. Graph this one right here, okay? All right, it says find the average rate of change of the two functions on the intervals 4 to 20. Enter the correct answers in decimal form without rounding. All right. Let's see if I can get my pen working here. All right, so 4 and 20, that's our x values. So if you remember average rate of change. All right, so this is on the interval. That means this is my x's. In this case, it's s for speed of wind, but these are both x values. So that's why I put them here and here. So what I need to do is find out what values go with that. So 4 and 20. So if I look over here at 4, 2, 4, this one has a y value of 20 as well. And at 20, it looks like it's about negative 10. All right, so I'm going to find the average rate of change. So I'm going to do negative 10 minus 20 over 20 minus 4. And that's negative 30 over 16. If I take my calculator and divide, that gives me negative 1.875. All right, so I want to use the same interval and look at the other line here, the red line. So I'm going to take the same interval from 4 to 20 on my x's, my speed of wind, and I want to see what my y values are. So at 4, it looks like this is 10. That would be 15, so it's right below 15. Let's say 14. And then at 20, I go up, and it's going to be, there's 10, that's 5. Let's say about 4. All right, so we're going to do y minus y, 4 minus 14 over 20 minus 4. And that's going to be negative 10 over 16. And negative 10 divided by 16 is negative 0.625. All right, so if we take those numbers, it says on the interval 4 to 20, the average rate of change for the first function, that's the blue one, that's over here, is about negative 1.875 Fahrenheit per 1 mile per hour increase in wind speed. On the interval 4 to 20, the average rate of change for the second function is about negative 0.625 Fahrenheit per 1 mile per hour increase in wind speed. Let's see if I need a 0 there. Okay, so negative 1.875. Pretty sure I did my math correct, so let's see if I just need to put in a placeholder. All right, good. All right, so compare the average rate of change of the two functions on the interval 4 to 20. What can you conclude? In terms of absolute value, the average rate of change of the first function decreases more rapidly than the second function. Okay, you can tell that because if you take the absolute value of these two functions, you're going to see that the first one is larger than the second one. All right, compare the key features of the graphs of the two functions. The second function's range is not as great as the first range, and you can tell that because it doesn't go as high and low. The second function has a 0 of 36, which is greater than the first function, and the two functions have the same value at